Hello everyone. Now it's the time to practice with linear regression and develop a simple linear regression model for a given data set. Now, as you can see here in the Wikipedia, the simple linear regression model is a model, as you can see, it's model that has some equation like y equal alpha plus beta x. It's a straight line equation. You can call it y equal a plus bx or whatever. And where x for us here is input, I like to call it input, and y is output. So y is a dependent variable and x is independent variables. So in general, when we build a model, we are expecting some input and some output. I would like also to show you the system identification process in general. Okay, just for the sake of understanding the whole goal or the whole operation that we do. System identification process is system identification, not recognition. System identification process is, I like this graph actually. It helps to understand what's going on. So you usually have some experimental data that is coming from different sources, and as we discussed, we could have this data from various sensors, and then we do a processing for this data, and we try to do that before using Panda, and then after that we select a model structure. In our case here today, we're gonna do a simple linear regression model, and then we evaluate this model and then validate it based on the data. So these are different, different characteristics of how to build a model like this. I think this one is from one of my papers, but in general, so your goal is always to build a model. Now, in our case, we're gonna build a linear regression model. So building a model here, what we mean by building a model is actually number one, selecting the structure. Number two is estimating the model parameters. So normally when we have a data, we expect that the data will be like X and Y, like two columns. These two columns describe when X has a value, Y has a different value. So this is, for example, a diagram that shows a relationship between X and Y, something like that. And then we will try to estimate the values of the. Of course, there is no guarantee that we will be able to estimate the accurate value for the parameter alpha and beta or a and b, because there is going to be always some kind of error in the model characteristics. Okay, of course, we can maybe try to uh, fakely create some data where we know the value for alpha and beta, and then see if linear regression will be able to find these optimal parameter. We can do that. Okay, but in our case here, what I'm gonna do is I'm gonna try to again retrieve some data from Panda, and utilize this data for some simple simple linear regression model development. And here we say that this here we call it beta 0, beta 1. Again, the name of the parameter should not be a conflict or a problem. So this is called the constant or intercept, and this is called independent variable. Okay, normally this is the bias that shift the value of y. Let's say for the value of x is 0, so this means beta 1 times x is 0, so y will be beta 0. This is the intersection of the straight line equation with the y-axis. So if beta 0 is 0, then it intersects at the origin point. And of course, if beta is 0 and we have beta 1x, so this means that this is going to be the slope. So beta 1 will be the slope of the straight line. Of course, this can be positive if we have a linear relationship between x and y, and could be negative if we have a negative relationship between x and y. So let's start. So simply, what I'm going to do here, I'm going to try to develop the linear regression model and fed the data for that model. And then what I'm going to do is I'm going to start to import the libraries. So we can say import pandas because we need pandas for the data frame as BD. And we can also import, as we do for plotting, import matplotlib dot by plot as BLT. Okay, that's the first. I'm gonna upload actually the required libraries step by step, so you can recognize these libraries at each time. So now I'm executing this command to plot it. Let me just adjust this input. Okay. So now I need to define the input and output for the model. And before I do that, let me just upload the data here. There is a nice data set called student scores.csv. It's available on Panda. So I'm gonna call df equals bd dot read read underscore csv, and then we're gonna load student underscore scores dot csv, right? And then let's, after we do that, let's show some part of the data. Let's show the head like this, and let's see what this data contain. All right, it seems that the data is not available on Panda. This one, I think I got the data from online, so I searched it on studentscore.csv. Then I go to this GitHub, and then from this GitHub I can say download. It's nice to know the procedure, and then I can download it here. I think I already installed, downloaded. It's called Student Score. So what I'm gonna do here, I'm gonna go back and then go to upload the data, students scores, okay.csv, and approve it. And then I'm gonna run this one. Here we go. So this is the data set that we have. Of course, as I mentioned, yeah, the other place where we can get the data set is Seaborn, but I'm just uploading this data from because I was checking to find like a nice data set, a simple one where we can apply the simple linear regression. We're gonna do an example which is actually have more than, like, multiple linear regression has more than input, because in our case here the hours will be the data set that we're gonna utilize as input like X, and the scores will be the output, which is Y, that we need to estimate. Let's do some kind of, like, say df dot shape to know how many samples are in this data set. I think it's very simple number, very oh, I called it data. Okay, so I have to call it data here. I have to call it data, not df. Here we go. So that's the size of the data is 25 times 2. So this is a data set. Now I need to define the x and y. To define the x and y, I have to do it like using the following. I'm gonna call x, this is x, I'm gonna call data, and use the command drop. So I'm gonna drop one column from this data, which is scores, which is the output. Okay, so I can just say scores. Let's make sure that the spelling is correct, and then say axis equal 1. What we do when we say axis equal 1, we actually dropping a column. If axis equals 0, we are dropping rows. And then y equals data dot not dot and scores. Hope this is correct. Yes. Now if I run this, here we go. So now we have the x and we have the y. I thought I called it df, but I changed that to data. If you want to call it df, let's call it df for simplicity reason. I like to call it df actually. And then I have to run this one more time, and then I have to run this one more time. Okay, and this one should be df. You know, in many cases we call it df. If you like to call it data, that's fine, but realize that is correct. Now, if this data is imported here, then I can check X. Here we go. So this is X hours. I can check Y. Here is Y. Okay. All right. Now we don't need this anymore. Now, after I did that, I don't need this Y. Did I move something here? No. Okay. Now, I would like for exploration, I would like to draw the relationship between the hours and the scores. So in order to do that, I would like to include a new command. Maybe it will help you. You can play with the size of your figure. So normally we call plot and then we call it figure. We call the figure. And then we would like to change the size of the figure. So we call fig size and then say equal. I tried several size of the figures to implement, but you can, this is the width and the height, so maybe you can change it the way you like or according to the screen size. And then I'm gonna plot the scatter plot actually, which shows the relationship between the X and Y because it's gonna be dotted. I cannot draw it as a line because as a line it's gonna be not helpful at all. And I'm gonna call scatter and I'm gonna plot X and Y, simply just X and Y, nothing more. And I can plot the label, X label. I can call it hours, and I can try label, and then I can say plot dot Y label, and the Y label will be the scores. Okay, and if you would like to add a grid, so you're gonna say plot grid and make it true, and then we're gonna say plot dot show like this. Let's look at this figure and see how it works. Okay, I made it like 4 times 4, as you can see. It's so I can see it in the screen. If you want to make it like, for example, 3,3, like size of the figure, so this will make it smaller so you can see it better. That's fine. So this is a relationship. As you can see, this looks like there is a relationship between the hours and score. It can be like a straight line in this position, and we need to find this the A and B, or beta 1, beta 0, and beta 1, or alpha and beta. So the 2 parameters, so we can build the best estimate. Okay, I like to call the actual response and estimated response. So Y that we have now is the actual response, and we would like to get the predicted response or estimated response. So in order to work with linear regression, we need to import some kind of libraries from scikit-learn. So I would say from sklearn, I would say import, and we're gonna import model selection. If you would like to, yeah, by the way, if you would like to import data from scikit-learn, you should say data sets. That's what I was planning to do at the beginning. So you can import data sets, and we would like to import model selection. That's what we need to import. And from the scikit-learn, sklearn dot model underscore selection, we need to import actually something called train test split. The train test split function actually is utilized to split the data into training data that we can use for building the model and testing data to verify the model quality or performance. Okay, now in order to do that, we need to calculate some criteria as we mentioned in the lecture. So we say sklearn dot matrices import. There are several criteria that we can utilize uh, uh, for evaluating the model performance or accuracy. Okay, these criteria can be, the most common one is the mean square error, mean squared error, and the mean absolute error. Of course, as you can see, there are many other criteria, but we're going to stick with these two criteria for simplicity reason. So we here are importing the data set. If you like to use the data set, if we already got the data set, as you see, you can remove this, no problem. Okay, and you don't need it. And then we have model selection. Normally after some time, what's going to happen is you're going to import all these libraries or all these required libraries at the beginning. So, but we just for educational purpose, we import it when we need it. All right. So now the next step is we would like to get the data set, which is X and Y, and split it to training and testing. This is a very simple command actually, as in Python. So I'm going to call the training data X train, and normally we use X capital and X test. And for Y, we commonly, use lowercase y. So we call Y train and Y test. And then we call the library which we just grabbed from the scikit-learn, train underscore test split, and we need to feed to this library X and Y. Not only that, but we need to identify the size of the testing data. So when we split the data, the most common split is we keep 80% for training and 20% for testing. Of course, this is not like a rule, but it's generally that's what we do. Maybe somebody can split it to 90% and 10%, 70%, 30%, 75 and 25. It's up to you. Okay, and then we say test size. So we identify the test size. In my case, I'm going to use 0.2 as test size. So this means that I have 80% for training. And then we need to define something called random state. Okay, you can get it from here, random state. And you can select any random value here you like to choose. And that will help if you run the experiments again, you will get the same shuffled distribution for the random selection. So you can select whatever value you prefer. Okay. So I'm going to do it like this. I'm going to upload the import to the packages, and now I did the split. I can test this if I would like to say what is X train, just in case. So here is X train. It's the hours, as you can see. Okay. All right. Now the next step is I would like to initialize the model, the linear regression model. I would like to initialize the linear regression model. Okay, to initialize the linear regression model, we have like very simple commands. Actually, we have just the three commands that we utilize. We call the model, we fit the model, we predict. That's it. So in order to use use the linear regression model, we need to import it from scikit-learn. So we again from sklearn dot linear underscore model. That's the way we upload it. Import, and it's linear regression. There we go. That's the command that we utilize. And then after that, I'm going to call the model. You can call it model. You can call it LR. You can call it LR small. You can call it LR model. I mean, whatever name you prefer, you can call it. I'm going to just for simplicity, I'm going to call it model, and then get this linear regression here, and that's it. That's the initialization of the model. Here we go. Now I was able to initialize the model. Okay. Now after I initialize the model, there is another command we need to use. It's called fit. Now I need to fit the model using what? Using the data model.fit. And basically I would like to use the training data and so the training input and the training output. Okay, so that's the two commands that's commonly used. Once we do the fit, actually, this will help us to calculate the intercept and the coefficient for that model. Okay, now I have the model. Okay, all right, so to see, now we are looking for like getting the value for alpha and beta. So I can say alpha equals model dot intercept, okay, and then say beta equal model dot coefficient. Here we go. Okay, if I would like to print the value for alpha and beta, I can say print alpha and then alpha and then print beta. Let me leave some space here, and this is beta. Okay, let's run this. Here we go. So this is a value for alpha and beta, which is the value of the coefficients that we have. Okay, so now we have the model, we have the alpha plus the beta times x. If I would like to display this, I think it might be a good idea if I would like to format the output alpha such that it produces like only like 2 digits. I think I can do something like that. So this is can be done in Python like this way. I can say colon 2f, like just two values, and then I say format dot format, and then theta, and I have to open quotes here, and there is a problem here I need to fix. Yes, I need to put dot so that I have the correct format. Right, I cannot do this format here because actually beta is an array of values. Here it's just one values. So I made a print out for the values like this way. This is alpha. Okay, and unfortunately this format is fixed for just the display, so we can make it here when we make the print only. Okay, now the next step is to calculate the actual and estimated response. This is very important phase here that we need to understand very well. Now normally what we do is we calculate the prediction value over the training and testing. This is what we need to do when we publish a paper or present a paper. We need to show the performance over both training and testing. So I'm going to define some variable. I'm going to call it y predict train, and I'm going to get the performance of the model. So model dot predict, and here, and I'm going to feed here x train, and I'm going to do the same thing for y, call it y predict test. So this is the value, the performance of the model over the testing data, and I'm gonna feed here the test data. Okay, now let's run this one. So it works fine. Okay, now I would like to draw this relationship for both training and testing, which is very important. So as we did before, in this case I would like actually not to draw like two different figures, but I would like to plot like sub plots or sub figures. Okay, this is one interesting features in MATLAB, and it's again here available in Matplotlib. So I would like to get you gain some experience on it. while we are doing, I'm trying to add some new comments. So I will say plot. First of all, I will define the size of the figure. So I will say plot figure, and then I'm gonna say fig size, fig size equals. Uh, I will try maybe 7 and 3. Again, this is it's optional. It's up to you the way you like. And then I'm gonna plot subplot. Let's plot subplot 1. As in do in MATLAB, we use a command called subplot, and subplot actually create a matrix of drawing. So if I would like to, again we use MATLAB, if I would like, let me show you the command subplot. And here we feed like 3 numbers. If I say 2 comma 2 comma 1, so what does this mean? It means I'm gonna draw like 2 times 2 subplot, like it's gonna be like a matrix. But in our case, and then 1 means the first plot. But in our case, we can just have one row and 2 columns. So we only have 2 plot here, subplot 1 and subplot 2. And then in order to draw the relationship between x and y at both training and testing cases, what we do is we use scatter. Okay, we use a scatter plot. Okay, not anything else, because if we draw line plot, it's not gonna work. Maybe if we can draw a bar plot, but bar plot again will not be nice. The best one here is scatter plot. And now I need to fit to the scatter plot 2 arrays of values that I'm gonna draw. So it's gonna be normally the y train and the y predict train. All right, y train and y predict train. Okay, and then of course I'm gonna use plot dot title, and I'm gonna say training case, and then I'm gonna say plot dot grid true. Okay, so that's gonna be the first subplot. Let me just copy and paste this and tell you what exactly you need to correct, but be careful when you copy and paste. So this will be 2, and then this 1 2, and this should be subplot number 2. If you missed it, it will do the 2 plot on 1 subplot. And then we're gonna call this test, and this is gonna be test. Okay, and this will be like testing case, not training case. So this will show us the values that was calculated based on the training case and based on the testing case. Show, and then we can do the plot. Here we go. So on the left here we're showing the training case. Of course you can, if you like to have the x-axis and y-axis, I think we can get it from here. I mean, you don't have to write it again. We can do it here, Control V, and here Control V, and then run this. Here we go. So this is our scores in the trading case, and this is our scores and testing case. If you feel like this is like the font size is like 12 is different little bit, maybe we can go here at the title and just say, if you remember, font size, and we can make it as 10, right? And here again we can go to the next title and make font size equal 10. That maybe will make it nicer. Here we go. So almost all of them are similar. Okay, now this shows the relationship between these ones. Now if I would like to calculate now with numbers the performance, there are 2 famous criteria, something called mean square error and mean absolute error. Let me just quickly show you what is mean square error equation or formula. It's very simple and straightforward. Here we go. So this is the formula. Okay, so the mean square error is what? Is the summation of the error over yi, where yi is the actual response, minus y hat, which we called as estimated response. And normally we calculate the error squared, because if you just subtract the error, in some cases it might be positive, in some cases it might be negative, and that will be canceled each other. So to make sure that the error is considered correctly, so we take the square root and then get the sum over all the samples from I equal 1 to n, and then divide this by n. That's why we call it square error, and then the mean of that square error. Again, here it is. So this is the mean of the square error. All right, so this is the criteria. Another criteria or formula is mean absolute error. I'm trying actually to show you how you can search for information online also. That's very important. If you didn't find something, you can search for it. Okay, this is the mean absolute error. Now, instead of taking the square root, you take the absolute value of yi minus yi hat, the actual and estimated, and then take the sum and divide it by n. So that's another way of making the calculation. Now let's go back here and see how we're gonna do that. Of course, in order to do that, we need to, we already imported, I think, the mean square error and mean absolute error. Let me see if we did that. No. Yes, we uploaded, yeah, we imported here. Okay, so you don't have to import it again. So in this case, what I can do is I can say the mean square error on the training case equals the mean square mean squared error. Okay, and then I'm gonna feed y train and y predict train. Okay, and then I can calculate the mean absolute error over the training case. Training equals mean underscore absolute mean absolute error, and then I'm gonna feed again y train and y predict trained. Okay, that's how I can do it. If you want to run this and see what is the mean square error and mean square error, we can just execute this command. And if I would like to see what is the mean square error and what is the mean absolute error, I can run this. Mean square error train should be mean square error train. Here we go, and then mean square error train. Here we go. So that's the calculated error, right? Let me just finish this. I'm just showing you the. Now I can take a copy from this, Control C, Control V, and then I'm gonna call this test, and this is gonna be test. Okay, and I would like to calculate this over testing, test. Here we go, and this is test, and this is test. Okay, now I can run this, so it works. Now if I would like to print this on the screen, I like actually to do something. I like to feed this data as to display this data as a data frame. If it is as a data frame, the nice thing is you can again take it and make a copy from that table to the table online and then display it in your paper. So I will say here create a data frame of the results, and this is a good brackets on the results, so I can say evaluate, or I can say performance. Okay, performance. Okay, we'll call it performance data frame. Okay, that will be bd dot data frame, and then I can define the data frame like this way. Okay, I'm gonna call the first attribute matrix, and then I'm gonna call it I have the mean square error, and then I'm gonna have another column which is mean absolute error. So this is in the training case and this is in the testing case. Again, mean square error and mean absolute error, then comma, don't forget the comma, and then enter. Now the second one will be the data type. So the data type that we have is the training and testing, right? So this is can be a list of train, here we go, train, test, and again train, test. You can highlight this one and put a comma like this, and then comma, and then the last one will be the values. Okay, and the values will be the mean square error train, mean absolute error train, and then mean square error test, and mean absolute error test. Okay, here we go. Let me see if that's correct. Let's run this. Okay, so it runs. Now I can call this performance df. Here we go. So that shows me the uh, mean square error in the training case, and then the mean absolute error in the, oh, I should have this train also train, because the values are coming one after the other, and this should be test. Okay, yeah, all right, here we go. I think maybe also if I do this as transpose, hopefully this will make it better. Yeah, what do you think? So this is a distribution. So in the case of training, the mean square error is 26. The mean square error in the testing is 48, which is expected the because the error usually over testing case might be bigger and the number of samples is less. Okay. Now for the sake of to check that everything is fine, I'm gonna do run all, make sure that we are getting the result. Now let me try something else. Let me try to go here when I do this train uh, test data. Let me make this like 50%. So I'm splitting 50% of the data for training and 50% of the testing. Let's see what's gonna be reflected on the final result. So this is training and testing cases. See that? And this become 25, right? And this become 32. So the numbers are changing. Of course, the more numbers, the more values or the more data we get, the better. Let's try 10% and run all. Here we go. So this is 30 and this is 20. So this goes down because the number of points here are less. So so the error was less. So, but I mean, like this is of course very small number of values, and it does not really reflect goodness or badness, because this is all are just 20 points or 25 points actually. So I don't think it's an adequate data set. By the way, here I can see that the accuracy is almost the same. Let's check this. So this is 26 and 48. Let's run it one more time. Yeah, 26 and 48. Yeah, because we fixed the random number generator. If we change this random number generator, for example, let's see what is the impact of this here. So it was 26 and 48. Here it is. So it changes because the samples are changing. So if you want to fix your results, that's something you need to make sure that it's achievable here. Okay. I hope this example is useful and it clarify what is simple linear regression. I'm sure we're gonna do some more examples on some more practical application for multiple linear regression. That next time we might go faster while we are doing that. Okay, thank you so much.